Hello everyone, welcome back to our Signals and System lecture. Today we will talk about lecture 2, which will be conducted on week 2 of your semester. In today's lecture, we will still be talking about introduction to signals and systems. However, we'll be more focusing on systems today. The module learning outcomes for today's lectures is still remain the same as last week's lectures, which is on LO1s to evaluate signals and systems to understand their properties. This is the outlines for today's lecture. It is very straightforward. It has the first part, introductions to systems, and the second part, different types of systems. So first, what is a systems? So according to Wikipedia, a systems is a group of items that is always interacting with one another and to form an integrated systems. And if you find the definitions from other source, most of the source will give you the same definitions, which is a group of independent items that react regularly to perform a task. And even from the textbook itself, it says a system is a combination of components that act together and perform a certain objective. So in overall, you can notice that many people has focusing on different groups of items. So groups of independent items or groups of independent components and combinations of them to perform certain tasks or to perform certain integrated environment. However, in mathematics or in the context of this module, a system is defined as a process where it has certain inputs and certain outputs. So in this case, the systems actually transform our inputs. For example, transform these inputs into a different output. So in mathematics, it can be written in this way. The outputs of the systems is a transformations of the inputs of the systems. So this is the mathematical representations of a systems. And so the next question is, where can we find systems in real life? And the answer is everywhere. So from the previous definitions, a systems must have an input and then it will produce a different output according to the inputs. And therefore, in our homes examples, aircon is a system, refrigerator is a system, oven is a system. In terms of transportations, we have cars, we have aircraft. So the inputs to the car, for example, will be how much you press the pedal, and the outputs will be velocities or accelerations of this car. And of course, we have engineering examples, astronautics examples, and even economics itself can be a systems. For example, how much people invest in economics, and then how well the economics perform based on the investments of the people. So in this slide, we'll be looking at different classifications of systems. So system can be classified in many different ways. One way is the static or dynamic systems. Then we can classify it as causal or non-causal systems, and then to linear or non-linear systems, and finally time variance or time invariant systems. So don't worry about each of these new words that you have just seen in this slide, because I will discuss each and every one of them in the following slides. And in our lectures or in this module, we'll be focusing on the so-called LTI systems. So LTI stands for linear time invariant systems, which fall into this category, linear and time invariant systems. So this system is very important as most of the systems can be studied through the properties of an LTI systems, and the analysis of LTI systems is very easy. So throughout this module, you'll be analyzing only on LTI system. Alright, first we look at the linearity of the systems. So for a linear systems, it is defined that it must satisfy two properties. The first property is called the homogeneity. Homogeneity meaning that any inputs that multiply by a constant. Here, this is A is any constants. It is same as the outputs of the functions multiply by the same constant. And additivities, which is the second properties of a linear system, is that any inputs, or we can say any two different inputs to the systems will have the same results as each individual's inputs to the systems and added up together. So as long as a system that satisfies these two properties, homogeneity and additivities, which combinations we call the superposition properties, this is called a linear systems. Whereas for non-linear systems, it is just any system that does not satisfy any one of the properties. Once it fails any one of the properties, we call it a non-linear system. So we can look at the examples in the next slides to verify whether a system is linear or non-linear. Alright, now let us look at these examples. Please find out which of the systems are linear and which of them are non-linear in these three different systems. So you are required to solve it on your own at home. The tips to solve this is to apply the homogeneity and also the additivity properties to all these three systems. And then you will notice that some of the system does not satisfy certain criteria. And those systems who are not satisfying that criteria will be non-linear systems. So I'll just give it the answer first. These two are actually non-linear systems, where this is a linear system. I hope you can get the answers by yourself. So in these next examples, we have a real life examples, which is a pendulum that will swing from one end to the other end, neglecting the air friction. So imagine you are swinging the pendulums in a vacuum. So these examples, if you do it mathematic modelings of these pendulums, it turns out to be of these equations, which is obviously a non-linear system because it has a sine functions over here. However, I mentioned that it's very important for us to study linear systems instead of non-linear systems. But most of the world examples are actually non-linear systems. What we can do here is that we can approximate these systems into a linear systems. So if you look at the graph over on the right here, I've plotted the theta against t. So, and obviously this theta against t is a non-linear system as it does not performs a straight line through the origin. So what we can do here is that we can make an approximations where the systems behave like a linear systems. So if we make that approximations, you will see that we can draw a straight line that pass through the origins and superimpose with part of this curve. So for examples, in the angles that's very small, let's say below 45 degree and above negative 45 degree. So let me draw out the angles. So let's say starting from here and ending here at these particular regions, if I draw a box out, you'll notice that this straight line superimposed with our curved line almost exactly the same. So we can make an assumption that the system is actually linear because this straight line is linear. So the assumptions only hold true if we have our angles to be very small. In this case, the angle must be smaller than 45 degree. And thus, our linear systems will have a different mathematical equations which can be analyzed through our analysis that we will learn in this course. So that is how we can convert a non-linear systems into a linear systems with some assumptions, and this is the assumptions, or this is the assumption, must be smaller than 45 degree. Alright, next is the time invariant systems against the time varying system. So what is a time invariant system? Time invariant systems is a system that has the output to be the same when you apply the same input no matter when you apply it. So it will be the examples on the left graph here. So in these examples, if you apply certain inputs at time equals to 0, the outputs behave as such. So this is the output. However, if you apply the exactly same inputs after certain delay, and it turns out that the output of the systems will be exactly same as the previous output. So this is kind of like a very good system for us to analyze, because you can analyze the system current time and you apply it on the future's time for this system. But there are some systems that is time varying. For example, the systems on the right here. It means that at current time, let's say at time t equals to 0, you apply certain input and it behaves like a blue curve here. However, if you delay it with, let's say, after 1 year, you apply the same systems, you apply the same input to the systems, the output will be different. This is called a time varying systems. So this systems is bad for analysis, meaning that any analysis that you do it now, it will be different when you do it after, let's say, after a few months or after 1 year. So in the next slide, you will see the examples of a time invariant system and also a time varying system. So for these two systems, which of them is time invariant systems and which of them is a time varying systems? I'll give you the answer first. For the first one will be the invariant systems, where the outputs will not change as long as you have the same inputs, no matter how much delay you put on the systems. So you can try to put t equals to t minus beta. In this case, t equals to t minus beta, and you'll notice that the yt here, you just substitute the t equals to t minus beta, you'll get the same answer. So however, if you look at the second examples here, yt equals to t times xt. So if you substitute t equals to t minus beta, you will turns out to be t minus beta multiplied by xt minus beta for the yt minus beta, which is different from just substituting this t equals to t minus beta. So therefore, for the second case, this is not time invariant system. This is in fact a time varying system. So I'll just write the vary here. And next is the causal system and non-causal systems. Causal systems is a systems where the output depends on only current input and past input. It does not depend on future inputs. So if you write in mathematical form, it will look something like this. The inputs will be current times or any previous time or any past time, and to form the current outputs. And on the other hand, a non-causal systems is a systems that depends on future output. So as long as the system depends on future output, doesn't matter whether it depends on present time or the past input, as long as it depends on the future inputs, it's called a non-causal systems. So you can see that realistically, you cannot have a non-causal systems to be implemented, because these systems depends on future inputs, which is not possible to be generated in a real physical system. Okay, now let us look at the examples. Which of the following systems are causal or non-causal systems? So remember, causal means that it depends only on present and or past input. Non-causal means it will depend on future. So this one, future must be here. Alright, let us look at the first examples. Yt equals to xt, and this is very obviously a causal systems, because these systems depends only on present input. So the output equals to current input. So the second examples, yt equals to xt minus 1, and if you look at t minus 1, as long as you have a minus here, it means that this is a past input. So the yt, the current output, depends on the past output. So this is again a causal system. Then the third examples, the yt depends on past input and present input. So again, it's a causal system. Now the fourth example here is a bit more tricky. This is an integration sign. However, if you look at this integration sign carefully, it is integrating the time from 0, which is the start of the systems, until current time t. So these particular outputs will depend on the presence, which is t, and all the past input, which is integrated from 0 to t. So this is again a causal system. However, look at these examples. If I do the integrations from 0 to infinity, and as I mentioned earlier, if 0 to t, these are the past input. T is the present input. So anything beyond t, from t plus 1 until t to infinity, this is the future inputs which you haven't gotten yet. So the example 5 will be a non-causal systems because it depends on future input. And now let us look at the last examples. Is a digital systems where the outputs depends on the next input. So n plus 1 is a next input. So it's against a future input. So this is a non-causal system. So in the previous slide, you learned about causals and non-causal systems. So for causal system, it must be the systems that depends only on present input or the past input and or past input. So it can be further split into two different systems called memory or memoryless systems. So for memoryless systems, it is a system that depends only on present input. So if you look at this example of resistor, the voltage of the resistors, it depends only on the currents that passes through the resistor at this present time. So it does not depend on any past currents that pass through the resistor. So this is a memoryless system. Whereas for systems with memory, we have one example here, which is the capacitors of the circuits. So a capacitors of a circuit is kind of like a charging up voltage. So it has the voltage depends not only on the present time t, the currents of the present time t, it also accumulates all the current that pass through the capacitors from the beginnings of time until the current time. So this is called a systems with memory, where it depends not only on the current time, but also depends on the past time. And so the dynamic and static system is just a different names to memory and memoryless system. So static systems is called memoryless system because it's static, it depends only on the current time. Dynamic system is called a memory system or system with memory because it is dynamic, it changes with time. Now if we look at the examples, which of the following systems are memory systems? Which of them are memoryless systems? So for any systems that depends only on current time, it is called a memoryless systems. So this one is a memoryless systems. And for the second system, it depends on the past time. And the third system depends on the current and past time. So these two are memory systems. Alright, so that is all you have to learn for today's lecture. It is a very simple lecture, only on the introductions of systems and different types of systems, where you have learned linear, non-linear, time invariant or time varying system, memory or memoryless system, and finally causal or non-causal systems. And in the next lecture, we'll learn about a concepts of convolutions, where you can passing through a signal towards a systems and how we calculate the output of the signals after passing through a systems, which is called the convolutions operation. So I will see you next week.